Okay, good morning, everyone, and welcome to our webinar on electrifying space heating in existing commercial buildings. We have a good program for you. There'll be 4 of us speaking, and then we'll have time for questions and answers. For questions and answers, please use the chat function, put in your question there, and we'll be sorting through those. And after the talks, we'll go through them and ask the questions. So please, as things are going, you don't have to wait till then. Start putting in your questions as soon as they occur to you, and that will allow us to sort them before when we get to Q&A. So my name is Steve Nadell. I'm the Executive Director of AC Tripoli and also the co-author of this report that was published last week that we'll be talking about today. My co-author, Chris Perry, will also be speaking about a lot of the technical information from the report. Chris is a program manager in AC Tripoli's buildings program. But then after the 2 of us co-authors talk, we'll be hearing from Charlie Jellin, who's an application engineer with the Trane company. He'll give a manufacturer's perspective because they produce many different types of heat pumps from the smallest to the very largest. And then we'll get an end user perspective from Josh Morjon, who's the energy manager at University of California, Davis, where they have done one project and are planning a much bigger electrification project. So with that, I will kick off with our presentation. I'm going to give an overview of what we looked at and what we found, and then Chris will go into some additional details. So for those of you who don't know AC Tripoli, we're a nonprofit research organization that is now celebrating our 40th anniversary. This slide has a little bit of information about us. I will not be reading all this information. Likewise, for many of these slides, I will not read every point. There is more points than I'll be making, but the slides will be posted after the webinar for those who want further details, or if you want to read the details while I'm talking, please feel free to do so. So to put things in perspective, in the U.S., there's a lot of interest in how we can dramatically reduce our greenhouse gas emissions and our energy use and ultimately decarbonize. This particular chart is from a study a couple of years ago by the Natural Resources Defense Council, looking at strategies for getting to 80% reduction by 2050 in greenhouse gases. What you can see here is the higher of the blue lines is what emissions might be in 2050 under a business as usual case. They looked at how much could be saved with energy efficiency, which is the lighter blue, cleaner grid and using renewable energy, as well as other no and low carbon sources, which is the light green, and then electrification of end use loads, which is the yellow. So the 3 of them together get us most of the way to the 80% goal. So electrification is one of the key strategies for helping to decarbonize the U.S. Looking strictly at the commercial sector, we decided to look at that because there's been very few studies looking at electrification in the commercial sector. A lot more in transportation, a lot more in residential, even some in industry, but very few in the commercial sector. Just to put this in perspective, if you look at commercial sector end-use energy, at the site level, about half of it is electricity, shown in gray. Natural gas is by far the second biggest, shown in blue, with smaller contributions from some of the other fossil fuels. Specifically looking at fossil fuel use in the commercial sector by end use, you can see that just over half is for space heating, with smaller fractions for water heating, cooking, and other. So given this, for this study looking at electrification of existing buildings, we focused on space heating because that is the majority of the fossil fuel use in commercial buildings. Now, commercial buildings have many different system types. Looking at across the top, we looked at rooftop units, which are units that typically provide air conditioning as well as heating, located on rooftops, typically on low rises, but not always the case. There are furnaces, which are moving to the right, the second one there, which, to oversimplify, are larger versions of residential furnaces. You have boilers, which boil water that get distributed around pipes to the working space. Those are some large boilers. They also come in smaller boilers. And then you have unit heaters, little things you may have seen in a service station or a warehouse that just blow air. So those are some of the main types that we looked at in this study. You can convert them to, looking at the bottom, into water source heat pumps, which you can see on the left. You can do various types of water loop systems and variable refrigerant flow systems shown on the lower middle, or there are also very large chiller scale systems that are heat pumps, as shown in an example on the right. So just wanted everybody to know kind of what system types we're talking about and what they look like. I would point out that rooftops, one of the most common ways to electrify is to do a rooftop heat pump. It's still a rooftop, but it is a heat pump rather than a air conditioner plus either electric resistance or gas heat. So to boil down our results into one single chart, we looked at the simple payback of installing a heat pump when the current system needs replacement. But the economics are much better at time of system replacement, not replacing a functioning system. What we found in our medium cost scenario, we also did a low and a high cost scenario, that in about 10% of the buildings that we looked at, and Chris will talk about the details, but we looked at a sample of more than 2,000 representative buildings across the U.S. And about 10% of the buildings, you can get a simple payback by installing a heat pump of 5 years or less. Another 17% is 5 to 10 year simple payback, but 3/4 are 10 years or more simple payback, including quite a few where the simple payback period is longer than the equipment life, and it just doesn't currently make economic sense. So there are some good applications for heat pumps today without any programs or policies, but it is a minority of the applications we found. We then looked at a set of scenarios that assume that you do energy efficiency to reduce the loads. In this case, we looked at reducing the loads by 20%. Also provide incentives such as through a local utility to reduce the upfront cost. We assumed $100 per ton of cooling capacity incentive. And in addition to that, we looked at what if there is a price on carbon that effectively raises the price of natural gas. If you do all three of those things, then 37% of the applications have a 0 to 5 year payback. Another 23 have a 5 to 10 year payback, for a total of about 60% that can pay back in less than 10 years with the program and policy scenario, but still another 40% that the paybacks are longer than 10 years. A few other significant findings. We found that in the building types that we looked at, we can reduce energy use by about 37% and greenhouse gas emissions by about 44% overall by installing heat pumps instead of the current fossil fuel systems. That I summarized the payback periods nationally, but they tend to be somewhat better in the southern U.S. and the Pacific region, where space heating needs are more modest, and in building types that often have higher operating hours, such as healthcare, food, retail, and offices. I'd point out that those things about the South or certain building types are general tendencies. we did look at a lot of specific buildings, and it does vary from building to building. Given what we found, it looks like electrification will proceed very slowly without policy support because so many applications have long payback periods. But as I noted, programs to promote energy efficiency will help, electrification incentives, pricing greenhouse gas emissions will help. If we start doing mandatory performance standards, as several cities such as New York City and Washington, D.C. and Washington State are doing, electrification can help meet those standards. We believe we also need research and development to help reduce the electrification costs, both in terms of improving the systems as well as improving the ease of which you can do the engineering and the installation. And one other idea that we thought of is, should we start encouraging bids for a heat pump when an existing heat pump system needs to be replaced, so people know at the time of replacement what the economics is for their site as opposed to our general tendencies. And ideally, if these are stored in some type of database, we can get a much better estimate of what the economics are than this study was able to do. A few other key findings. For some of the buildings with challenging economics, it may not be an all or nothing proposition. As we'll hear a little bit later, some of the case studies use fossil fuel as a backup for those very cold days. It doesn't have to be 100%. You can still, in many cases, displace a large majority of the fossil fuel use with the heat pump, but keep the backup. I would also note that our analysis also uses the current natural gas system as a base. If we are going to be decarbonizing, I know the gas industry is starting to work on a decarbonization case involving gas-fired heat pumps and use of what they call renewable natural gas. That would be a very useful comparison that we didn't look at. I suspect that will be quite a bit more expensive than the current natural gas system, but it would be an alternative case to look at for decarbonization. And, from analyses I've seen elsewhere, that would significantly improve the economics if the alternative case were different. Just wanted to wrap things up with a couple of case studies that are featured in the report. To give one example, a firm called Vichy Tansator. It's a mixed-use light industrial facility in southern Vermont. They presently had a 10-ton rooftop cooling and heating system that was at the end of its life. It used electric resistance. They looked at an electric resistance system, a propane system, and a high-efficiency heat pump, and chose the heat pump. What they found is that by going to a heat pump, they had about a simple payback period of about 4 years relative to either the electric resistance or the propane system. To give another example, the city of Vancouver in Canada has been retrofitting their city hall. It's a multi-phase retrofit. In the first phase, they installed a packaged chiller heat pump system that provides heating, cooling, and hot water, but they still have the gas boiler to provide additional heat on the cold days. They'll be doing a second phase to retrofit additional parts of the building and allow the heating system to take advantage of lower temperature water. Typical boiler water is quite hot and hard for a heat pump to reach, but if you modify the distribution system, you might be able to take advantage of lower temperature water that heat pumps can provide. Have some statistics on how much energy use and greenhouse gas emissions this project will reduce, and they estimate about a 7-year simple payback on their heat pump investment. So that's one example of a small rooftop system as well as a large chiller-based system. So with that, here's some contact information for both Chris and I if you have questions that we aren't able to answer afterwards. And for those of you who haven't voted, please don't forget to vote today or tomorrow. With that, let me turn it over to Chris to pick up with some additional details on our analysis. Take it away, Chris.
Great. All right. Well, thanks, Steve. Steve gave you some high-level takeaways from our research and some good case studies, and I'm going to touch briefly on how we set up the study, some assumptions we used, and some more targeted results. Before we dive into that, gotten a few questions, and I got an email about difficulty using the On24 platform that we're using. If that's the case, we've found it's helpful to hit the refresh on your browser button. For instance, sometimes slides don't move correctly, or if you can't access Q&A. So try that and see if it works. If not, let us know in the chat. We can see if we can help on a one-off basis. So, all right. So this is our methodology slide. I apologize for all the text. I know it's hard on the eyes. It's the only slide like this. And you can read through afterwards if you want. But basically what we were trying to convey here is that our analysis is based on the EIA CBEX data, Commercial Building Energy Consumption Survey data, which is made up of 6,700 buildings, and they are weighted to represent 5.6 million US commercial buildings, so representative of the entire US commercial building stock. For our analysis, we looked at the buildings with certain system types that use fossil fuel heating, and we'll describe those more in a few slides, and Steve already touched on them briefly. And so those system types, those buildings, they represent about a third of the 6,700 buildings in CBEX. And what we did was we calculated the economics and the energy and emissions changes and how those change when these systems are retrofit. We retrofit the fossil fuel heating systems with high efficiency heat pump systems. And we made a number of assumptions about the existing systems, including their age, efficiency, and size. And we also subtracted out any savings that you would get from retrofitting with a new fossil fuel system that meets current minimum energy efficiency standards. And we conducted our analysis below, medium, and a high cost scenario. And then, like Steve was mentioning, included scenarios where there were energy efficiency upgrades to the building, carbon price, or utility incentives. And one thing we wanted to emphasize was that heat pump sizing and performance changes a lot depending on temperature. It's more difficult for heat pumps to extract heat from cold air than it is from hot or mild air. Although this technology is continuously improving. And CBEX doesn't have data like average winter temperature, but they do have something called heating degree days. And essentially the higher the number of heating degree days, the colder the area that you're in. So we correlated performance, like you see here on this chart, with COP, and then sizing with capacity with the heating degree days. And so, based on what we just talked about, it's probably not too surprising to you then that we found that the paybacks were better in the South Pacific in what we're calling the hot mountain area. We divided up mountain into hot and cold because, Arizona is very different than Montana. And so these are the replacement scenarios that we evaluated. Number one, replace packaged fossil fuel rooftop units with packaged rooftop heat pump units. Like Steve mentioned, this is an extremely common system type in commercial buildings. The second was fossil fuel furnaces and central air conditioners replaced with split or packaged heat pump systems. These are more smaller systems, more residential size, so they would be in smaller commercial buildings. The third type is boilers or space heaters with central air conditioners, room air conditioners, or no air conditioners, replaced with ductless or variable refrigerant flow, VRF heat pumps. We were trying to represent systems that would most commonly be replaced with ductless or VRF systems. And then the fourth is the large built-up central boiler and chiller systems. We didn't actually complete an analysis for this. We found it to be very site-specific, and there weren't enough trends to really conduct a analysis like we did the other three scenarios. And so here are some of our high-level findings. First two scenarios, the packaged rooftop systems and the replacing the furnaces and central air conditioners with packaged or split system heat pumps, paid back pretty well. They paid back more than 50% of the time with no incentives. And I'm framing this a little bit differently than Steve did. This is paying back within the equipment lifespan, and whereas Steve gave it to paying back within 5 years or 10 years. So this is a little bit more generous framing. But you can add in carbon price, utility incentives, and more efficient buildings, and it really improves quite a bit and pays back the majority of the time in these scenarios. Our third scenario with ductless or VRF, the economics were more challenging. They paid back less than 10% without incentives, If you add in incentives, carbon price, and more efficient building, it increases to about 30%. But I want to acknowledge, I think it's important that we acknowledge some of the limitations of our study. So for one, we didn't consider the interactive effects of the like a VRF system with a dedicated outdoor air system, which can greatly improve the efficiency of the VRF system when those two are paired together. Also, the first cost for a VRF or ductless mini split retrofit is a lot higher in a new building because of the installation of the refrigerant piping. And some of the systems that we compared it to in this study were relatively inexpensive, particularly space heaters or room air conditioners in buildings with no cooling at all. So this could be an area for further study to better understand the best retrofit scenarios for ductless and VRF systems. And then for the fourth study, we found that there were a variety of systems that could be retrofit in large buildings. I think we might touch on those a bit more with Charlie and Josh's presentations after me. And then just to quickly touch on building types, some of the building types with the best paybacks are really some of the primary commercial building types you'd think of: office, retail, food sales, education. And you might ask, well, what doesn't pay back then? That's more likely to be something like a warehouse or a public assembly type building that is used less frequently or has relatively low space conditioning loads. And I know we ran through a lot in a short amount of time, but if you have any questions, feel free to reach out. We can go into more detail and describe our methodology a bit more. And so with that, I want to turn it over to Charlie, who's an applications engineer at Trane.
All right. Thank you, Chris. Thanks, everybody, for hopping on the webinar today. Charlie Jelen coming to you live from a cabin in Wisconsin. Happy to be here. We're going to walk through some of the product side of the research that Steve and Chris did. And I just want to start out, there's a lot of different ways to electrify a building. Heat pumps are getting a lot of attention right now because of their potential to save energy over their alternatives. We're going to talk a little bit about that on the next slide. But what I'm showing you here is there's 4 general categories that heat pumps are going to fall into. All right, so you've got air to air, water to air, air to water, and water to water, right? So it's what is the source or the sink you're working against, and where is that refrigerant going? Direct to the airstream or to a water, all right? On the bottom is a little bit more specific, an example of what type of heat pump that is. So if you look at air to air, rooftop heat pumps, VRF systems, package terminal heat pumps, right? Those are all examples of air to air style heat pumps. Like Chris was just talking about, we typically see air to air on the smaller scale, so either residential, light commercial, or getting up into a little bit of the larger commercial stuff. But as we move to the right on this graph or this chart, that's where we start to see larger commercial, more of your applied hydronic systems. All right, the second one there, water to air, classic example is water source heat pumps, right? Those have been around for a really long time. But water source heat pumps by themselves are not all electric for the building. Right? If you think about a water source heat pump system, there's also a condensing loop or a common loop that goes to all the heat pumps. And on that loop, there's usually a cooling tower and a boiler. Right? That boiler is there to condition or temper that loop during the middle of winter. So what you could do, and this would be a great potential what we're seeing for retrofit opportunities, is if you have a water source heat pump system and you're looking to electrify, you can go to an air to water heat pump, the next category, to start to either offload that boiler or totally replace that boiler. What I'd say is air to water heat pumps, that category is probably the one that's getting looked at the most. The reason being, on the commercial side at least, the most is because it's the most like a boiler or a replacement for a boiler that is out there for a heat pump. Okay, and then on the far right-hand side, water to water, a couple different ways to do this. You can do it with a reversing valve or without. I'd say most common is without, so it's basically just a water-to-water chiller. But you can control either the leaving condenser or the leaving evaporator. I know some of the cool equipment that's coming out right now are pieces of equipment that combine multiple categories. So combining an air-to-water and a water-to-water heat pump so that you can both heat, cool, and do heat recovery all within the same piece of equipment. All right. What I want to talk about next is some challenges, all right? And this is challenges that we see customers facing using heat pump technology. All right, and the first one is cold climate operation. All right, and Chris talked about this as what they used as part of their study is as ambients get colder, heat pumps in heating mode become less efficient. All right, and you'll typically hear people say heat pumps are 3 to 4 times more efficient than electric resistance, which I totally agree, but it's also dependent on that ambient. All right, so a COP, coefficient of performance, it's a ratio of what you get out versus what you put in. Okay, so electric resistance, COP of 1. And this is just a general example. This isn't any specific equipment that we're showing here, but at 45 degrees for this example, the COP is 3. That means you get out 3 times as much as you put in. That's the big advantage for heat pumps over electric resistance. But you can see what happens as the ambient starts to go down, right? If you look at 15 degrees, the COP is 1 because the power input went up, the capacity output came down. All right, so these types of performance curves from manufacturers are critical for designers because this is how you're going to size the equipment for your specific application. Another thing that needs to be known from the manufacturer is defrost. All right, because there's going to be a defrost D rate for each piece of air source heat pump equipment. All right, and if you're not familiar with defrost, there's an outside coil that we're pulling BTUs out of the outside air. All right, so you think of that, we're essentially cooling down the outside air outside. All right, and if that coil temperature is below the dew point, you'll start to condense. And if it's also below 32 degrees, it'll start to freeze. All right, too much frost on that coil degrades performance, and you potentially get a lockout scenario, which you want to avoid. All right, so what we do is we reverse the cycle of the refrigeration circuit. We send hot refrigerant out to the coil, we melt the ice, and we go back into normal operation. All right, but there's a D rate associated with that needs to be known upfront for sizing. The next thing is, I said this before, is air to water heat pumps are getting looked at for a lot of electrified jobs, specifically on the hydronic side. But if you think about a big building in a big urban setting, you probably have a boiler stuck in your basement, right? That's what you're doing all your heating from. If you want to replace that boiler with air source equipment, that's equipment that needs ambient air, do you have enough space to fit all of that equipment? And if you don't, the question becomes, where else are you going to get that heat from? And that's where we see a lot of innovative designs coming right now. All right, so what I have on the screen is just a couple different areas that people are looking at. Geothermal, top left, people have been doing this for a very, very long time, successfully, efficient. The questions become is, do you have enough space for it? And do you want to pay for it? The second one, building exhaust. Again, this has been used a lot, but there's been a definite uptick in designs using building exhaust as a source of heat. So the first one there, direct cooling of building exhaust, that's just a hydronic coil in your exhaust airstream, pulling BTUs and using it for heating. The second one on the right there, that's a really interesting one that we saw in Canada. They actually had a row or a bank of air to water heat pumps, and they were in a penthouse. And the building took all the building exhaust and routed it up into that penthouse, like underneath it. So it might be minus 20 degrees ambient outside in Canada during the winter, but that penthouse is at 75 degrees. All right, that's an awesome spot to run a heat pump in heating mode. So that was a cool application. Top right, wastewater. We're seeing more people try to use this, either the building's wastewater itself or tying into like a district storm or sewer drain and pulling BTUs out of that wastewater. The last one, storage source heat pump. This is an interesting one that we're seeing in bigger cities. If you have a building that goes from heating and cooling through the course of a day, this would be a great setup to try to conserve all your BTUs from the building. So the setup would be in the morning. Let's say you have morning warm up for an office building. In the morning, you're going to run a chiller and make ice. You're going to build ice, and you're going to take that, what would go to the cooling tower, that rejected heat, and you're going to send that to the building for your heating loads. And then as the building transitions throughout the day into cooling mode, that's when you're going to start to melt the ice. All right, so you're going back and forth with your BTUs throughout the day from ice to no ice. All right, but in general, there's a lot of cool strategies going on for electrified designs on where we can pull heat. The next challenge, and this is the first question I ask whenever we talk about all electric designs, is do you have a 8760 load profile, and do you trust it? Because sizing becomes critical with these types of systems. So what you see here is it's an 8760, but it's sorted by cooling load. So biggest cooling load first, all the way to no cooling load, and then you overlay your coincident heating loads. And what this gives you is this area in purple here, and that's the recoverable energy hour by hour. And that's huge for any high performance design and for any all electric design. Recovering as much heat as you can is going to be critical and potentially huge on first cost for sizing your equipment. All right, so that's a big one, is being able to get a load profile for both cooling and heating that you trust. The last one, and this is, Steve and Chris, their report it was on space heating, which makes sense. But there's also another system in the building that consumes a lot of gas, potentially. And that's potable or domestic hot water heating. So I just want to throw one slide on here, because a lot of the equipment that you use for space heating will not work for potable or domestic water heating. All right, and there's three main categories that we see for this type of heating: either electric resistance with a storage tank, a packaged heat pump with a storage tank. So there's a hot water storage tank that has a heat pump right on top of it. And then split heat pump is the picture that we're showing on the right there, where inside you would have a hot water storage tank, and then outside you'd have an air to water heat pump that's heating that hot water. All right, so that equipment is available, multiple manufacturers in the industry. So that's all I had. Next, we're gonna toss it over to our closer, Josh from UC Davis.
So I'm coming to you from California. It's going to be over 80 degrees today, so hope that doesn't make you feel too jealous. But UC Davis, a little bit of context real quick. It's over 5,000 acres. It's the largest UC in terms of land. We do have a lot of buildings as well, because we're came from ag history, so a lot of ag buildings, but about 120 of them are on our central heating and cooling. I'm going to mainly talk about our district heating and cooling. So this is kind of looking at heat pump, heat recovery at a larger scale and an application of that. But for those of you who have a campus or experience with campuses, just wanted to give you some context. Our annual utility bill is over $20 million, and just electricity and gas. And then we have a typical daily population over 30,000. Of course, that's typical. Right now, our quarter is remote, so most of the students are not on campus, but we do have, we're probably at 10 or 15% population of normal right now. And we have a goal that is carbon neutrality. Actually, the whole UC system has this goal by 2025, which is coming fast. So how are we planning to get there? Well, this shows kind of what's called a wedge chart, and each campus has done this with their planning process. The 2025 goal is super ambitious, but the good thing about it is that it pushes us to do the planning and think through the different scenarios. It looks like we're going to be having to use some offsets, at least initially, but we have biogas purchases as well. The UC system has purchased some ownership in biogas. But what's great about it is kind of the steps that we go through to get there. And the first step is efficiency. Looking at existing buildings, how do we waste less energy, waste less energy, use our energy more efficiently. Once we've done as much as we can do there, then we're in a better place to look at electrification. And that's a big piece of our plan. We have an additional piece, being a campus, where we really strive for the engagement and education part of it. I'm a big proponent of thinking about the reason the buildings are there. It's for the occupants. And so we want to always try to engage the occupants in the process. We have things like a thermal feedback app where we take feedback from occupants and buildings directly, so we can not just optimize around energy, but around occupant comfort and aim for productivity, things like that. But that's our general strategy. Part of the electrification is definitely renewables. That's something everybody's always going to when they think about electrification. We do have, this is a picture of our campus, but down on the bottom of the picture there, on some of our converted ag land, we have a 60-acre solar farm over 16 megawatts. I think it's the largest on-campus solar farm in the U.S., maybe the world, I don't know. But we also have another 30 megawatts off campus. It's a big part of our strategy with hydropower and other things. We're going to be at 100% electric, 100% carbon-free electric supply this next year, most likely. So that's a part of our electrification strategy, is to green up our electricity supply. But for us, the big challenge is really the fossil fuel side of it. This is just a picture of our dashboard that shows our electric demand in the green, and then the light green or yellow bumps on the bottom showing that the output from that on-campus solar makes up a good part of our daily supply to the campus. But overall, we have about a 40% of our carbon footprint is tied up in our heating system on campus, which is a natural gas-based steam heating system, as is similar on a lot of campuses across the U.S. So we're doing what some other campuses are also doing or have done, which is convert that steam system to hot water. And so I just wanted to briefly touch on the why we're doing that. But we're changing our district energy from a steam system to a hot water system. And this shows here the whole campus on that district energy system, kind of broken into colors for the different districts and how we're phasing the project to do the conversion. And we're currently implementing this one in red that shows the red pipelines that are getting installed as we speak. That's putting in new hot water pipelines to the buildings from our central heating and cooling plant. And then we're going to attack the other parts of the campus. We're doing this in steps because we're a public university and we don't have the funding to do the whole thing at once. But we're also trying to be really strategic about how we do it so that we can get the most bang for our buck. So the first project we're doing is putting about 30 buildings on hot water, which eliminates some of our losses on the steam side. That's a big benefit. But then the next step is we're going to be putting in heat recovery chillers. So let me talk about that. And that's one of the big reasons why we want to go to hot water. And Charlie talked about this as in terms of potential sources of heat. When you have a district cooling system, that is probably your best source of heat, because that district cooling system, like we have with our chilled water system, is collecting heat from the buildings. And that heat right now is getting thrown away in our cooling towers to the atmosphere, but that's a huge potential source of heat if you can get to a lower grade heating like hot water. So this is showing on the positive axis our cooling demand, that 8760 demand that Charlie was talking about, shown over the course of a year from January to December. You can see our peak cooling is in the summer, obviously, and then our heating load is shown on the negative y-axis, and that's higher in the winter. The red there right now is showing the heating load that we can't do with heat recovery, but the orange and the light blue is showing our heat recovery, or the simultaneous heating and cooling, that load that we can serve with heat recovery. Chillers are essentially heat pumps at a larger district scale. And so then the question is, once you've gone to hot water and have eliminated the losses on the steam system, which was running at 350 degrees, and now we're down at 150 to 160 degrees distribution, then, how do you make that hot water? And heat recovery being the obvious one. There's also a lot of other options out there. And that's one of the main reasons we're doing this project. And this is just a graphic that our consultant, AEI, out of San Francisco, has put together just to show some of the potentials. I'm not going to talk about all of these, but this shows kind of how the system works. And a big benefit of having the hot water is that you can do thermal storage. We're doing right now thermal storage with our cooling system. And that allows us to do things like load shifting. That's been very beneficial. Even in the rolling outages we had this summer, we're able to take 10, 12 megawatts off the grid with our thermal storage. But it's even better when you can do things like seasonal load shift, or in our case, we can't do seasonal, but we can certainly do daily load shift. And on these shoulder seasons like today, we've got a 40-degree morning and an 80-degree afternoon. And so we're able to do heating in the morning and cooling in the afternoons, and we're storing that heat during the day and storing the cooling at night. And we're going to be able to meet about 50 to 60% of our heating load with heat recovered from our cooling side. And the question then is what are the other renewable or carbon-free ways that we can meet our peak heating load in the winter when we don't have enough heat recovery from the buildings? And these are some of the areas we've looked into. It may be too small to see everything, but what it shows is that, initially we're recovering heat from the buildings. There's some easy ways to do that even more. For example, we're going to be looking at closing down our airside economizers and extracting more heat out of the buildings. It's counterintuitive. You typically want to use those airside economizers to reduce mechanical cooling, but if you can pull more heat out of the buildings when you have a heat recovery chiller or a heat pump, then you can actually get a significant more amount of heat in the winter from those buildings. But there's other things like that chilled water. When we can't heat it up in the buildings, we don't have any more heat to extract from the buildings, we could run that heat into the ground, run that chilled water into the ground and pull it out at a warm enough temperature to do heat recovery. So that'd be called geoexchange. But you can do other things like Charlie mentioned with wastewater, even domestic water. We've looked at solar thermal. That there's a couple different ways to do that. The challenge there is that it overlaps with our heat recovery. And so heat recovery for us is more cost effective. But we're going to still be exploring a lot of these options, and they can be incremental. When we have the hot water infrastructure, we can tap into a lot of different low-grade heat sources to extract heat and help us to meet those winter loads and get off of fossil fuels and meet that carbon neutrality goal. So while we look at electrification in our building construction, we've converted my own office on campus from packaged systems to a VRF with DOAS and LEDs and fully electric building. We look at new construction going that route in some cases, but when we have a district energy system like this, in many cases, it's more efficient and more cost effective to try to electrify the district energy system and have your buildings tap into that. So I'll put that out there, and if people have questions, I'm happy to talk more about those, but I'll wrap up my presentation for now.
Great.
Okay, great. Thanks.
Go ahead, Steve.
Oops. I was going to thank Josh. We've gotten quite a few questions. I know we've been trying to answer some of them, but I was trying to save a few of the ones that might be a broader interest for the group. Chris, I thought I'd start with a few of the ones I put at high and then turn it over to you as we start going through some of the others, if that works.
Sounds good.
So one of the questions is, what about high-rise buildings? What about complicated buildings? We looked at things like rooftop systems, VRF. In our report, we have a whole chapter discussing those systems, but it's just a discussion about what is possible, what are some examples. The economics of converting a large building are highly site-specific, and we did not do an economic analysis on these. We do recommend, as one of our recommendations, that we need a good engineering study that picks a representative sample of, say, 100 of these buildings and really looks at them carefully, but that's going to require some detailed engineering and not the type of analysis we were able to do. So those are very important. It applies to high rises. It applies to many of the larger campus buildings. As Josh discussed, we were just able to do discussion. Another question we got was, what about the peak demand of all electric systems? And yes, those could be substantial. In places like California, where it's a large summer peak, from what I hear from my California utility friends, that's probably not a big issue. Sure, maybe it is around Lake Tahoe, but by and large not. But as you start moving to the northern U.S., they are projecting that as heat pumps increase, the peaks, instead of being summer afternoons, may be early mornings on winter days. And there will be definite peak demands. I know I was involved, along with Synapse Energy, on a study looking at what are the peak demands if everybody converted to heat pumps during a polar vortex, and they can be quite substantial, but you can also help reduce them through energy efficiency, through demand response, and through the use of backup heat when the temperature gets really cold. But there will need to be some beefing up of the grid to handle winter peaks in cold areas, and how much you seek to manage those peaks will depend how much beefing up is needed. But it's definitely...
Sorry, Steve, I was going to jump into before we moved on. I think
Please.
That we had several questions on the grid impacts, and I think it's worth spending a little bit more time on this one. For sure, like we didn't assess what those impacts would be, but we know that this is an emerging issue, and we wanted to plug DOE's Grid Interactive Efficient Buildings Program, or GEB as it's referred to. So it's essentially the idea that buildings, through smart and grid connected technologies, also while being energy efficient, connect with resources for the grid to help mitigate some of these high peaks. Whether that's load shedding or shifting the load to a different time. This is going to become more of an issue as as electrification policies increase, as we see more heat pumps, electric vehicles. More solar PV. So the more resources like buildings that we can leverage to help the grid, the better.
Great, thanks, Chris. I was going to deal with two last ones before turning it over to Chris and others. Do we know of any studies looking at new construction? In our report, we cite a new construction study looking at the residential sector, which shows that the economics tend to be better in new construction because the costs are lower if you're building new than retrofitting. Also, you can save the cost of a gas distribution system within the building and to the building if you're able to go all electric. We did not look at new construction. We do recommend that there be a study. We suspect that the economics will be better, but we did not examine that. And then we had a variety of questions, a comment saying, well, we used a 10-year simple payback as a rough dividing line. 10 years simple payback is, like an 8-9% internal rate of return, which some people consider pretty good. We've had other comments saying anything beyond 2 years, payback gets very difficult. We use that as a rough approximation, but each building owner will have different criteria. And if you have one that, 5, 6, 7% return on investment, it works. Great. A lot more will be cost effective. On the other hand, if you really have one that needs a 50% cost of return, your opportunities for electrification will be limited. But we do provide in the full report, full distributions, as just in the summary that we kind of use 5 years, 10 years as breakpoints. With that, Chris, why don't you take some of these?
Sure. So I saw a few questions come up during Charlie's presentation. There seemed to be some interest in the in wastewater heat exchange. So I'm going to ask one that I feel like is pretty representative. So this question says, would like to hear more from Charles whether wastewater heat exchange is a real emerging tech trend we should be paying attention to, or is a concept still less developed stage? So where is it on the spectrum?
Yeah. I'd say it's fairly developed. If you look at the European market, it's a technology that they use at both the building level and at the district level. So there are some European manufacturers that you can partner with them here in the U.S. I do know of 2 that are in North America. So I'd say it's available. Where it is on the maturity scale, I don't know. But yeah, it's definitely available to use. Working on 2 different jobs right now where it's being implemented.
That's cool. And I've seen one in person here in DC, a zero energy building, the National Geo, I forget what headquarters it was, but it was really, really cool. And I think that they had to, get it from Europe shipped essentially.
Yeah, and there's a couple different ways to do it. There's wastewater, where you're actually screening out waste, getting to the water component, and then using the water as a source. There's also other ones that are focused more on your building you can imagine if you have a lot of hot water that you're using in your building, that's all just going down the drain. So capturing that water in some type of holding tank that has an indirect heat exchanger on it, where you can hook it up to a water-to-water heat pump, great source of heat recovery.
Yeah, it was American Geophysical Union, by the way, just remembered. All right, so question for Josh here on, is UC Davis planning for a microgrid for reliability and resilience given California's grid issues?
Yeah, that's a good question. Our campus in particular hasn't had as many issues because we happen to be on a distribution line for California rather than transmission line, or actually a transmission, I think, rather than distribution. But we basically have not been turned off at all in the past number of years, and aren't part of the public safety power shutdown. So reliability for us has been something we've looked at a lot, but it's not been to the point where we need to make the whole campus an island or anything like that. It's also very challenging at the campus scale to do anything like that. So we're more looking at strategies to deal with large outages and how we keep critical buildings online, things like that. So some of the other campuses in the UC system have definitely had more issues with that, but that's not really been our main priority. We do have microgrid on small scale, like campus buildings. We've done some research level microgrids.
Great, thanks. Yeah, there's I noticed a lot of questions come in on reliability and resilience. So we might revisit that topic if we have more time. One other comment I'd have on that is I think the biggest piece for us has been having storage. Being able to do thermal storage, I think, is a very helpful thing in terms of resiliency. And that's one thing that having district energy as well as heat recovery, I think, is a big help on that front. Great. All right, so we also had a number of questions come in about refrigerants, and so I'm going to direct this to Charlie here. Got a few different ones. I think this is a pretty good broad question. So to what extent is uncertainty about future refrigerants making it more difficult for Trane to project future COPs? So how much? I'd say more broadly, how much are you taking the future changes in refrigerants into account with these technologies?
Yeah, good question. If you look back to the past, and we're going through a refrigerant transition right now. So if we go from R11, let's just take low pressure refrigerants for now. You go R11 to R123 to 514A or 1233ZD. The efficiency has gone down slightly, but we're only talking a couple percent. So I don't think going forward, especially with some of the refrigerants that we have available now, which we call them ultra low GWP, 0 ODP, so GWPs of 1 or 2, we can make up for the couple percent loss in the refrigerant efficiency with better heat exchangers, better compression cycles, just putting more copper in it too. That helps. It's more expensive. But I think long term, I don't see refrigerants or chiller efficiencies or heat pump efficiencies going backwards because of the refrigerant.
All right, thanks. So I'm gonna take a question. I think this one could be for any of us. It started with me or Steve, but can you save money or emissions in colder climates when space heating is converted from natural gas to electric? And so, this question is I'm reading this as like, how does this apply? I live in a colder climate, could this apply to us? And I think it's like anything, it depends. I think it depends. Well, I guess to back up, yes, based on our analysis, you can save emissions, certainly. I think money is a little bit difficult because of what we talked about with the reduced efficiencies of heat pumps at cold temperatures. But I'd say there's a lot of different things at play here, and we're seeing the technology evolve quite a bit. And we're also seeing, a lot of policies that help support it. So, to me, this is an emerging area, and I think some areas right now definitely can be cost effective, but I would think in the future more so. Steve, do you want to address that maybe?
Yeah, it really will depend a lot on the relative price of gas and electricity. It tends to be better for buildings that are heated with propane than with natural gas. It depends on the local price of electricity. There are quite a few buildings in our sample that contribute to that portion of buildings that do have reasonable paybacks that were in cold climates, but the better paybacks are much more so in the south. But there are some examples where it will pay back in the north, but it very much depends on those local prices. I'd also note in response to some questions that in the north, we generally did assume use of some of the best cold climate heat pumps currently available. We did not assume the same heat pump everywhere, but we try to look for current units with good cold climate performance.
All right. So, and I guess I would open that, Josh or Charlie, do you have any thoughts on that? Anything that we haven't already addressed?
Sorry, what was the original question, Chris?
It was about colder climates, and are there energy or emission savings in cold climates? And I guess Josh,
I can't really speak to that. Yeah.
I'd say one thing that I could add to that is, I think a lot of people go into this thinking it's all or nothing. It's either we're going all electric or we're not. And I think there's going to be ample opportunity for reduction instead of elimination at the beginning. So if you don't have a heat pump that has full capacity at -15, it's not the end of the world. There's other things. There's electric boilers. You could use the existing boiler that's there and start by offsetting as much as you can without the intent of eliminating from the beginning. Because I think that's a big hurdle to get over for a lot of applications.
All right. So something else we got, this is directed at me and Steve more, so our 20% analysis for cost, did that include building envelope measures? What was our 20% energy efficiency analysis? And then the comments is we found that, building envelope measures help quite a bit. And I think that's probably a good thing for us to address as an energy efficiency organization. We agree. We see a huge improvement in building HVAC system if you have a building with a tight envelope. And our energy efficiency analysis try to take that into account by allowing the capacity of the HVAC system to be reduced. That's how we accounted for it in our calculations. And then we assumed a 5-year payback for those increases. It was just kind of a proxy. But yes, we believe that building envelope upgrades will help space heating and space cooling quite a bit. And that was included in our analysis. Anything to add to that, Steve?
No.
All right. So we have time for maybe
2 more minutes.
Yeah. So here's one that came in for Josh that I thought was kind of good. So looking at your decarbonization plan for UC Davis, what amount of that is, gas offsets versus building electrification? How does that divide out?
Yeah, well, so energy efficiency is a big piece of what we're doing. We're trying to do as much as we can on that front. That's most of what my team works on. I would say, that might be 20% of our overall plan. But then I think that this electrification of our district heating system is probably 40%. Because so much of our heating right now so much of our carbon footprint is tied up in our heating system. As far as new building electrification, most buildings that are being built right now are either tied into our district system, and so they're going to be electrified once that system's electrified, or we are doing some electrified buildings that are not on the district system as well. So that's a small piece of it, but it is something we're working on as well. And it has its own challenges. I could talk more about like the maintenance side of it can be a challenge for a campus environment where we have our limited refrigeration shop, and they're now having to take care of a lot more refrigeration equipment. But that's probably more specific to campus environments.
Great, thanks. So we are at time, and we had a ton of questions come in. We didn't get a chance to get to quite a few of them, but we will try to reach out, if possible, after this to get back to you. So with that, we want to say thank you for attending the webinar. Steve, any final words?
Nope, thank you very much. This is an area with a lot of interest. We see our study as just an initial take on this, as shown by many of the questions. There's a lot more work to be done, whether it's new construction, large built-up systems, et cetera, and just trying to understand even the smaller systems much better. So we consider this the initial stab at this work and not the final conclusive answer. But thank you all for your interest.